Hey guys, welcome back. We'll continue with the book Python for Data Analysis. In this video, we're going to cover data cleaning and preparation. This is part of a multi-part series, so if you haven't already, feel free to subscribe to the channel. Let's jump right in. Let's dive into data cleaning and preparation. If you want to follow along, you can head over to wesmckinney.com/book and read the book for free. We're going to start out by covering how we can handle missing data. Then we're going to focus on data transformation, extension data types, and finally string manipulation and working with categorical data. Now, before we can actually dive into data analysis, we typically need to load, clean, and rearrange our data, and this can take up to 80% over the overall time. So it's really important to have this down. Let's first have a look at how we can handle missing data. Now, in a lot of cases when we are doing data analysis, some of the data may be missing. And one of the goals of pandas is to make working with missing data as painless as possible. Now, by default, when we work with pandas, missing data is represented as NaN, which stands for not a number. Let's open up our terminal and let's dive into IPython in order to have a look at an example. And to start out, we are going to import pandas and we're going to use the alias PD for abbreviation. We also need NumPy, so we are going to import that as well, and we are again using the alias NP. We can now go ahead and use pandas in order to create a new series object with 4 different values. And inside of that, we're going to use NumPy in order to create a not a number value, so a missing value. If we have a look at our float data object we just created, we can see that indeed the third value here at index 2 is missing, so not a number is displayed. As we saw in a previous video, we can use the method isNA in order to return which values are missing, so which values are null. So in this case here, the third value again at index 2 returns true because it's not a number, and in all other cases we get back false because these are of course actual values. Aside from NaN, which stands for not a number, and NA, which stands for not available, we also have the value none we can work with, which is part of Python. Now if we create a new series object with none as one of the values, and we have a look at that, we can see we have the value NaN and none in the second and third position, so at index 1 and 2. And if we now use our isNA method, which is checking which value is not available, we can see that the second and third value, so NaN and none, are both counted as missing values, and therefore true is returned, and for all other values false is returned. Now a lot of times, of course, we want to filter out the missing data in order to properly do our data analysis. And to do that, we can use the dropNA method, which is going to remove all values that have missing data. So let's have a look at an example. We are going to create a new series object here, which has 5 different values, but 2 of those values are actually missing. So if you have a look at our data object, we can see at index 1 and at index 3, not a number is displayed. Now to easily remove those values, we can simply use the dropNA method, and that is going to return all actual values, but the missing values, so values that are not available at index 1 and 3, have been removed from the output. Now if you're working with a data frame object instead, there are different ways to remove missing data. So for an example, let's create a new data frame object, which contains of 4 different lists with 3 values each. So if you have a look at our data object that we just created, we can see that multiple values here are missing. And just as with series objects, we can go ahead and we can call the dropNA method. And this is going to remove all the different rows where at least one missing value is included. So in this case, we can see that only the values in row with index 0, so the first row, are returned because in every other row, at least one missing value is included. Now, if we want to be less restrictive and maybe only remove a row if all of the values are missing, we can provide an optional argument. So in this case, instead of simply calling dropNA, we can pass the optional argument how, and we're going to set it to all. And if you have a look at that, we can see that in this case, only row with index 2, so the third row, is removed because in this case, all the values are missing. But we still get back the row with index 1 and the row with index 3 because there's at least one actual value in that row. Now, so far we looked at removing rows from our data frame. We can of course also remove columns. For an example, let's first of all add an additional column, column 4, which we're going to set to not a number. So if we now look at our data frame, we can see we have an additional column here, column 4, and all of its values are missing. Now we can remove those columns by using dropNA again. But in this case, we specify that we don't want to look at the rows, which is a default behavior, but instead we are going to set access to columns. And then again, we specify that we only want to remove the columns where all the values are missing. So in this case, this is only going to remove the last column because here all the values are missing. And importantly, this does not modify the original dataset, but simply returns an updated data frame. That means if we look at data again, we can still see that the column actually exists in the data frame, only the returned value here would be modified. Now, rather than just removing missing data, as we've been doing so far, we can instead also just fill in the missing data with some other data. So for example, we could say that for all the missing data, we want to replace those values with a value 0. And for that, let's have a look at an example. We're going to create a new data frame object, and we're going to use NumPy's random method in order to create a 7x3 data frame. So if you look at our data frame, we can see we have 7 different rows from index 0 to 6 and 3 different columns. But let's update this data frame. In this case, we're going to set the first 4 rows for column 1 to not a number. And after that, we're going to set the first 2 values in column 2 to not a number as well. So that means if we look at our data frame again, we can see we now have a bunch of missing values. Now, if you want to fill in those missing values, we can use the fill_na method. And as an argument, we are going to pass the value that we want to replace those missing values with. So here we are specifying a value of 0. That means we can now see that for all of the missing values, we instead set the value 0. We can also use the fill_na method and we can specify a dictionary that we pass as an argument. So in this case, for the column with index 1, we're going to set the values to 0.5. And for the column with index 2, we're going to set the values to 0. So now we can see for column 1, the missing values are indeed set to 0.5. And for the last column here, all the values that are missing have been set to 0. So far in this video, we have covered how we can handle missing data. But apart from working with missing data, we often need to filter, clean, or transform our data in some other way. And the first operation we're going to take a closer look at is to remove duplicates from a dataset. So for an example, let's jump into IPython and let's create a new data frame object, which has 2 different columns, K1 and K2, and a total of 7 different rows. In the first column, we're going to have different string values, and in the second column, K2, we're going to have integer values. So let's have a look at our data frame, and we can see we have 7 different rows, 2 different columns, and while the values in K2 are repeating, so for example, we have 1, 1, 3, 3, 4, 4, in K1, we have also repeating strings, for example, 1, 1, 2, 2. But if we look at the different rows, we can see that typically those values here are different, except for the last 2 ones. So here we have 2, 4 and 2, 4. So for the row with index 5 and 6, we have exactly the same values. In order to easily find those duplicated rows, we can use the duplicated method, which we call in our data object. And this is going to give back false or true, depending on whether the data is duplicated or not. And this method looks at each individual row and compares it to the previous rows to see if the same values occurred in a different row. So we get back false for all rows except for the last one, because here the values for the row are the same as for the previous row. Now, to easily remove those duplicates, we can use the drop duplicates method, which we also call on our data object. And this is going to return an updated data frame. And here we can see that the duplicated row, so row with index 6, has been removed from the result. And by default, our drop duplicates method considers all the different columns and compares all the values. If we only want to have a look at a subset of the columns, we can provide an optional argument. So let's have a look at an example. And we can add an additional column to our data frame called v1. And for the different rows, we are simply going to pass range 7, which is going to assign the values from 0 all the way up to 6 as the associated row values. So let's have a look at our data frame again. And we can see we have an additional column added with the values from 0 to 6. Now by default, if we were to use drop duplicates, it would compare all the column values. And since for column v1, all of the values are different, none of the rows would be dropped. But let's say we want to look at column K1 and simply look if there are repeating values. We can see that we only have 2 different values, 1 and 2, and they're simply repeating. So if we are going to use our drop duplicates method and we are specifying the argument subset and setting it to K1, note that we are using a list here, then we are only having a look at the unique values inside of the K1 column, and we are going to drop all duplicates. So by doing that, we can see we only get 2 rows back, because after row with index 1, the values are repeating. So 1, 2 are the unique values, and then we are simply repeating those values. Now, removing duplicates is a pretty straightforward way to update our data set. There are also other ways of transforming our data by using a function or a mapping. And to have a closer look at that, let's create a new data frame. Our data frame is going to have 2 columns, food and ounces, and we are associating different kinds of foods with the respective weight in ounces. So let's have a look at our data, and we can see the different kinds of foods here and the associated weight in ounces. And if you have a closer look at our food column, we can see these are all different kinds of meats. And let's say we want to add an additional column to indicate which animal each of those meats came from. So for that, we can specify a new dictionary, and we're adding the meats that we specified in the column before as a key. And as a value, we have the associated animal that the meat comes from. Now, in order to associate the meats with the respective animals, we can use the map method. We saw the map method before in a previous video, and basically what we do here is we specify a new column animal, which is going to be part of our data frame, of course. And as a basis for that, we are going to use our food column that we specified before, and then we're calling map on it, and map accepts a dictionary as an argument, and we are passing meat to animal as the argument. Now, once we have done that, we can have a look at our data object again. And now we can see we added the additional column animal. And based on our dictionary that we defined up here, the foods are properly associated with the correct animal. So the map method is a really convenient way to perform element-wise operations. Now we can also replace values. We saw before that we can fill in missing data by using the fill_na method, which is a special case of replacing values. And while we also saw that we can use map in order to modify a subset of values in an object, we can use the replace method, which provides a simpler way to do that. So let's have a look at an example. And again, we're going to start out by creating a new series object. And here we are adding 6 different values to our series object, and we're going to store that in data. So if we look at data, we can see we have 6 different objects with index 0 all the way up to index 5, and these are float values. Now, looking at the data, we can see that we have -999 that occurs twice, and that might be a value which actually stands for missing data. So in order to highlight that a little bit better, we can use the replace method, and we are going to replace value -999 with not a number, just to make clear that this is actually not a valid value, but a missing value. So by doing that, we can see that we easily replaced -999 with not a number. But maybe we want to go further and we want to make sure that we remove all of the negative values here and replace them with a different value. So in this case, we want to replace not 1, but 2 different values, -999 and -1000. So in that case, we can simply use our replace method. And as a first argument, we are going to include a list of values, which contains both of the values we want to replace. And again, we are going to replace it with not a number. And this is going to replace all of the specified values here with NaN. Now we can also replace those 2 values with different values. If you want to replace -999 with not a number and -1000 with 0 instead, then we would simply pass 2 different lists to replace. The first one containing the values that we want to replace, and then the second one containing the values we want to replace the actual values with. So in this case, we can see we got not a number for the entries where we had -999, and -1000 is replaced by a value of 0. Now when we work with data frames, we have different axis indexes we're working with, and we can also rename those without having to create a new data structure. So let's have a look at an example. We are going to create a new data frame object, which is going to use the arange method in order to create a range from 0 to 11. And based on that, we are going to create a data frame with 3 rows and 4 columns. And for the index, we're going to use the labels Ohio, Colorado, and New York. And for the columns, we're going to use the labels 1, 2, 3, and 4. So if you look at our data frame, we can see this is what we get back. Now let's say we wanted to transform our row labels here, and we wanted to change them to all uppercase, for instance. And let's also say we wanted to do the same for the columns here. See, we also want to display them in all uppercase letters. To accomplish that, we can create a new function called transform. And the transform function here takes an argument, and we're going to take that argument, look at its first 4 values, and then call the upper method on it in order to change the value to uppercase. Now once we define that function, let's use our data frame, and we are first of all gonna get its index, and then we're going to call the map function and pass transform as an argument to it. And by doing that, we can see that the index label here for our rows has been changed to uppercase. Now, in order to actually update our data frame, we can then call data.index and then basically associate the values we get back by calling that map method and passing transform to it and storing that back in our data index. So looking at data now, we can see that we now changed the case for our index values for the different rows, and all of those are now displayed in uppercase. Now, if we want to create a transformed version of our dataset without actually changing the data frame itself, we can instead use the rename method. And here we're specifying that for our index, we are going to call the title method, meaning we're going to capitalize the first letter and all the other letters are going to be in lowercase. But for the columns, we want to call the upper method, which means that the values 1, 2, 3, and 4 should be displayed in all uppercase letters. So looking at that, we can see that indeed Ohio, Colorado, New York are now displayed in title case, so first letter capitalized and all the other letters in lowercase, but the different column headers here are now displayed in uppercase. We can also use our rename method in order to change the labels themselves. So for instance, here we are changing the index, so the rows, from Ohio to Indiana, and for the columns we're going to rename column 3 to Peekaboo. So let's confirm this, and now we can see that indeed Indiana is now displayed, and we also renamed our third column here. When we are working with continuous data, for example a list of ages, we often discretize or otherwise separate the data into bins for data analysis. So let's assume that we have data about a group of people that we are studying, and we want to group them into discrete age buckets. So let's assume this list here contains the different ages for the group of people we are looking at. And let's say we want to divide those into different buckets. We're going to define the variable bins, and we want to divide the number of users into buckets from 18 to 25, then 26 to 35, 36 to 60, and then 61 to 100. For that we can use pandas cut method, and that method takes two arguments. First of all, our list of values that we want to section into different bins. So in this case, our list of ages. And then as a second argument, we need to provide the bins, so the sections which we want to use to categorize our age data. And we're going to store that back into age categories. So if we now have a look at our age categories, we can see we get back a list of 12 values. Those 12 values are exactly the number of entries we have inside of our ages variable. So it means we have 12 people in our dataset that we are taking a closer look at. And down here we can see the different categories that we defined. So here we can see our first category is from 18 to 25, then 25 to 35, 35 to 60, and so on and so forth. And we can always see on the left side are parentheses and on the right side are brackets. Brackets means this is inclusive. That means here we are looking at the range 18 to 25, including 25. And parentheses means this side is open or exclusive, meaning we are looking not at 25 itself, but 26 to 35. And then we can see the individual sections here. So for each of those values, we can see which categories they belong to. So here, for example, the first value 20 would be inside of the range 18 to 25. The same is true for the second category here, and also the third one, because 25 is inclusive in this range. After that, 27 would be in the next category, so 25 to 35, and so on and so forth. Now, if you only want to have a look at the categories, then we can use our age categories variable and call categories on it. And here we can see again our categories that we also see up here. So the 4 different sections into which we subdivided our age ranges. Now we can use the value counts method and pass our age categories as an argument to it to quickly determine how many values fall into which categories. So here we can see in the range from 18 to 25, we have a total of 5 values. In the next section we have 3, then again 3, and between 61 and 100 we only have a single person. And of course we can briefly verify that. If we look at our ages, we can indeed see that if we look at, for example, the section from 61 to 100, we only have a single value in that range. And if you compare that to the range from 18 to 25, we can see that we have 1, 2, 3, 4, 5 values in that range. Now, if you want to take those categories that we defined here and we want to associate them with different labels, we can do so. For that, we can define different group names. So for the range from 18 here to 25, we can call that youth. For the range from 26 to 35, we could call that young adults, then middle-aged, and then senior. Next up, we can use our cut method again. And as before, we are going to pass ages and bins as arguments to it. But as an additional optional argument, we are going to set the labels to the group names we just specified. And now we can see we have those 4 different categories here, and those labels are displayed instead of the ranges that we saw before. Now in this example, we used specific bin categories that we defined that we passed as an argument to pandas cut method. But let's have a look at another example where we're working with 20 random values that we store inside of a data variable. And if we take a look at that, we can see we have those 20 values, which are all values between 0 and 1. Now we can use the cut method again, but in this example, we're going to pass our data object as the first argument to it. This is the same what we did before with the ages list, but as a second argument, we are now simply providing integer value rather than predefining certain buckets. And we are also passing precision as an optional argument and setting it to 2. So this means that we are not basically looking at the entire range of those values, but we only have 2 decimal values that we are looking at. So by providing an integer value here as a second argument, pandas is automatically constructing the different categories based on the dataset. So in this case here, we have the range from 0.04 up to and including 0.25. Then 0.26 to 0.49, and so on and so forth. So this can be quite useful since pandas is able to save us some work and basically section the data automatically based on the values and the ranges included in the dataset itself. Now we can also section the data based on quantiles. So let's use the random method again, which is part of NumPy, to create 1,000 random values between 0 and 1. So looking at that, we can see that we have a very large dataset to work with. Now next up, we can use pandas qcut method in order to cut our data into quantiles. In this case here, we are providing the data as an argument, so those 1,000 values we just generated. Then as a second argument, we are going to provide a value of 4, which is going to cut our data into sections of 4. And again, precision is going to be 2 decimal places. And we're going to store that in quartiles because we provided 4 as a value, so we are sectioning our quantiles into sections of 4, so quartiles. Now looking at those quartiles, we can see we have those 4 categories here, and we can see we have those ranges here from negative 3.23 to negative 0.67, then up to negative 0.032 to 0.6 to 3.14. And we can see the category ranges here are not necessarily the same size. And the reason is that the qcut method, other than the cut method, sections the data based on the number of elements that we have in each category. So it basically ensures that we have roughly the same number of elements in each of the different category sections that we define. So if you want to make sure that we have roughly equally sized buckets, then the qcut method is the right way to go. And of course we can verify that by using our value counts method from before and passing quartiles as an argument. So looking at that, we can see that in this case, each of our buckets has actually the same number of values, so 250 for each of those different sections. If you want to make sure that we have the same distance in each of the categories, we can use the cut method. If instead we want to make sure that we have roughly the same number of values in each of our categories, we would use the qcut method instead. But similar to the cut method, we can also specify our own quantiles that we want to look at. So in this case here, rather than passing an integer as the second value, we are specifying the quantiles we're looking at. So qcut accepts data as the first argument as before, and the second argument here specifies the quantiles. So meaning the first section here is going to have 10% of the values, so 0 to 0.1. Then the second part here is going to accept values between 0.2 and 0.5. So 40% of the values. Then after that, we're looking at 0.5 and 0.9. So again, 40% of the values. And in the last category, we have values between 0.9 and 1. So 10% of the values. And if we then call value counts on it, we can indeed see that now we sectioned our data differently. We have 100 values in the first bucket here, 400 in the second and third, and again 100 in the third category. Now when we work with large datasets, we need to be able to detect and filter for outliers. So let's look at an example, and we're going to use pandas and NumPy to create a new data frame with 4 columns and 1000 values. And now we can use the describe method on the data we just created in order to have a look at the relevant data. So we can see we have our 4 different columns here. Each has 1000 values included, and we can see what the mean, standard deviation, and the different quartiles, as well as the minimum and maximum value equals to. So let's say we want to have a closer look at column 2. So we're going to take the data in column 2 and assign it to the variable col. And now let's say inside of that column, we want to have a look and find values that exceed the value of 3 in absolute values. So for that, we are calling the absolute method on our columns. We are checking if it's greater than 3. And of course, we want to get the results back inside of our column. Now in this case, we can see we have a total of 5 different values, which have an absolute value that's larger than 3. Now, in order to select all rows that have an absolute value greater than 3, we can use the any method, and we're specifying as an optional argument that we are looking at the columns. And of course, we want to have the absolute values that are larger than 3. And this gives us back all the different rows where at least one value is larger than 3 or smaller than -3, because we're looking at the absolute value. We can also randomly reorder a series or the rows in a data frame. And to do that, we can use NumPy's permutation method, which is part of the random module. So let's have a look at an example. We're going to create a new data frame object, which we're going to store in the variable df. So looking at our data frame, we can see we have 5 different rows and 7 different columns. Now, if we want to reorder the rows inside of our data frame, we can use the permutation method, which is part of the random module, which of course is part of NumPy. And here we are passing a value of 5 because we have 5 rows. And we're storing that back in the sampler object. Now let's take a look at sampler, and we can see we now have an array here with the values randomly reordered. So in this case, 4, 1, 0, 2, 3. Now we can call the take method on our data frame, passing sampler, the array we just created, as an argument. And this is going to rearrange our data frame. And we can now see that the rows have been reordered based on the new order that we got back by using the permutation. Of course, we can also do the same with the different columns. So here we are using the permutation method, passing a value of 7 to it because we have 7 different columns. So this would be the new random order of our columns. And now we can call the take method again, passing our column sampler as an argument. And we also need to specify that we want to change the order of the columns because by default the rows would be adjusted. And looking at this now, we can see that the new order that we got back and saved inside of column sampler is now applied for our columns. Now the final data transformation type we want to look at is the ability to compute indicators and dummy variables. And this type of transformation is quite important for statistical modeling and also for machine learning applications, because it allows us to convert a categorical variable into a dummy or indicator matrix. So let's look at an example. We're going to create a new data frame with 2 columns, key and data1. And of course we can have a look at that data frame, and we can see we have 6 different rows and the 2 columns we specified. Now we can go ahead and we can call getDummies on our data frame, and we are passing the first column key as an argument to it. We are also specifying the data type to be of type float, because by default it would be of type Boolean. Now based on that, we're going to get back this output here. We still have our 6 different rows from index 0 up to index 5. Now we have 3 columns, A, B, and C, and they all have a value of either 0 or 1. And the way this works is as follows. We can see that inside of our key column here, that we provided as an argument, we have the values A, B, and C, which correspond to the 3 different columns that we now have. And we are basically looking at our index here and checking if the associated key occurs at that index. So looking at column A, for example, here, we can see that the key A only occurs at index 2 and at index 4. So that means here at 2 and 4, we have a value of 1 and all other values are 0. If we look at B, we can see this occurs at index 0, 1, and 5. So these values will be 1 and all other ones will be 0. And of course the same is true for column C. Here this only occurs 1 time at index 3. So this is set to 1 and all other values are set to 0. And we're going to take a closer look at the getDummies method at a later point when we look at modeling. Now the pandas library was originally built upon the capabilities that were present in NumPy. And NumPy primarily was working with numerical data. It is however also possible to work with extension data types, which extends the default types supported in pandas. Now if we look at an example, we can create a new series object with 4 different values, one of which is a missing value. And if we look at the series object, we can see that it's of data type float64. And float64, the data type, is mainly used due to legacy reasons. But we could use a different data type instead. So we could create the same series object, but specifying a data type as an optional argument. And here we're specifying the data type to be of type integer64. So looking at our series object, we can now see that we have data type integer64, and the missing value here is represented as an A, standing for not available. Pandas also has an extension type specialized for string data, which does not use NumPy object arrays. For example, we can create a new series object which contains the strings 1, 2, 3 and one missing value. And as the data type, we are going to specify string data type, which is part of pandas. Now we can look at our series object, of course, and we can see it's of data type string. And the benefit of using strings here is that they generally use much less memory and are often computationally more efficient for large data sets. We can of course also manipulate strings, and Python has long been a popular raw data manipulation language, in part because it's very easy to perform string and text manipulations. So let's first have a look at Python's built-in string object methods. And for an example, let's create a new string, which has those values A, B, then some spaces, and then Guido. Now if we want to separate that string based on a certain separator, we could use the split method. In this case, we are splitting based on the commas. So whenever a comma occurs inside of our string, this will be split into individual values. And as we can see, we get back a list of values, and those are split based on the comma separator that we provided as an argument to the split method. Now the split method is often combined with the strip method to strip whitespace, such as over here. So as an example, we can split our string based on a comma, and then for each of the values that we get back inside of our list, we are going to call strip to remove the whitespace. So if we now look at pieces, we can see we have A, B, and C, and the whitespace has been removed in front of the string. Now if you want to go ahead and then join the values in pieces together again, we can do so. For that we would use the join method, and we can specify the separator between each of those different strings that we are joining together. So in this case here we are using 2 colons, meaning if we do that, we can see we have A, B, and Guido, and we are joining it with 2 colons in between. We can also perform Boolean operations. For example, we can check if a certain substring is inside of a string. So here we are checking if Guido is inside of our values variable, and that of course is true, so we get that back as a Boolean value. We can also determine where a certain value occurs. So here we are using the index method to check at which index inside of our values variable a comma occurs. And if we check for that, we can see this occurs at index 1. So this is exactly what we would get back. We can also use the find method to find where a certain substring occurs inside of a string. So here we are checking where colon occurs inside of our string. That of course does not occur at all. Therefore we get back a value of -1. And if this was a value that occurred, we would get back the index. So for instance, if we do that with a value of A, we would get back 0 because at index 0 we actually have the substring A. We can also use the count method in order to count how often a certain substring occurs inside of a string. So here we are counting the occurrences of a comma. And of course the comma occurs twice, so this is the value we get back. We can also replace a value with a different value. So for instance, we can replace a comma with 2 colons, which will give us back an updated version of the string. Now in order to save on time, we can use regular expressions. And regular expressions provide a flexible way to search or match string patterns in a text. And to work with that, we can use Python's built-in re module, which is responsible for applying regular expressions to strings. So let's have a look at an example. We are going to import the re or regular expression module. And let's have this example text that we're going to work with. We can now use our regular expression module, specifically its split method. And inside of split, we are providing a regular expression as an argument. And then as a second argument, we are providing the text Now the regular expression here basically states that we want to remove the white space that occurs inside of our text. And \s stands for the white space. And the plus operator here means that we are matching one or more occurrences of it. So that means we are going to remove the white space, whether there's a single white space that occurs here or whether there's multiple white spaces. And \t, so the tab space here, would also be affected by that because it's also basically a white space. So by doing that, we can see we get back a list of values and remove the white space from the string. Now, aside from Python's built-in string methods and aside from regular expressions, we can also use string functions which are part of pandas. So for an example, let's create a new dictionary called data, and we can now go ahead and turn that into a pandas series. So if we look at that, we can see that we have two columns here, one consisting of different names and another one consisting of email addresses, one of which is empty. Now, based on that, we can use pandas strings methods. So for instance, we can use data.string and then use the contains method to check whether the email address contains Gmail. And here we can see that for the first value, it returns false because we don't have gmail.com but google.com. For the second and third value, we return true because indeed we have the substring Gmail. And for the fourth value, we get back not a number because we don't have a valid value here. We can also use regular expressions with pandas. So as an example, we have quite a complicated regular expression pattern. And this pattern basically matches email addresses. So we can see, for instance, that we have the @ sign here, and then we have a period. And we basically ensure that in front of our @ sign, we only have allowed characters such as A through Z and 0 to 9. And after the period, the domain can only have a length of between 2 and 4 characters, and it has to be letters from A to Z. And this way we can determine if a provided email address is actually valid. Now we can use pandas string method, specifically the findAll method, and we're going to pass the pattern to it. And as a second optional argument, we are providing a flag, and here we are using regular expressions in order to ignore the case. And here we are getting back the valid email addresses. Now, pandas also has a special categorical data type, and we can achieve better performance and memory use when we use pandas operations. Now let's have a look at an example, and we're going to create a new series object with a number of repeating values. So if we look at that, we can see that the values for apple as well as for orange occur multiple times inside of our series object. Now, in order to identify duplicates, we can use, for instance, pandas unique method, passing values as an argument to it, to have a look at the unique values so we can see the unique values are only apple and orange. We can also use the value counts method in order to get back how often apple and orange occurs inside of our series object. Now, many data systems, such as for data warehousing or statistical computing, have developed specialized approaches for representing data with repeating values. And one of the best practices often used are dimension tables, which store the distinct values and integer keys. So let's have a look at an example. We are creating a new series object, and that series object of values only contains values of 0 and 1. And then as a second series object, we can create dim, which contains apple and orange, so the two values we saw before. And now we could simply have a look at our values object, which only contains integer values, and therefore is easy to store and access. And on the other side, we have dim, which only contains two values, apple and oranges. And using both in combination, we can easily restore the series object we saw before. For that, we would simply use the take method, which we call on dim, and we pass values as an argument. And this is easily going to restore the same series object we had before. But using that dimension table that we created with the values, we improve performance and we also reduce the memory needed to store the values. Pandas has also a special categorical extension type for holding data that uses the integer-based categorical representation or encoding. And that is a popular data compression technique for data with many occurrences of similar values. And again, this can lead to faster performance and lower memory use, especially when we work with string data. So let's have a look at an example. Here we are defining a list of fruits. And again, we have apple and orange. And looking at that, we can see that those values repeat quite a number of times. we're going to store the number of entries in our fruits list inside of n. Then we can define a random number generator, and we also provide a seed in order to get back the same result if we need to. And based on our fruits list, we can now go ahead and create a data frame. So here we're defining different columns: fruit, basket ID, count, and weight. And we're using our random number generator to create a random value for the count as well as a random value for the weight. So let's have a look at our data frame. And here we can see we have 8 different entries. We have the fruit, so apple or orange, and we have the count, random value, and the weight, which is also a random value. Now, in order to convert that to a categorical extension type, we can take our data frame for the fruits and then call sType on it, passing category as an argument. And if you now look at our variable fruitCat, we can see that the data type is of type category. We have our entries of apples and oranges, so the 2 categories here, and of course the associated index. And using those categoricals, we can use certain methods. So for an example, let's create a new series object. And as before, we are going to call sType and pass the argument category in order to turn this into a categorical. And let's verify that. So if you look at that, we can see we have our series object here, of course, and the data type is category. We can now use the special accessor attribute cat in order to access, for instance, the categories codes. And we can also have a look at the categories themselves. So here A, B, C, and D, and of data type object. And quite often, when we're using statistics or machine learning tools, we'll transform categorical data into dummy variables. So taking our category data cat_s, we can call getDummies, which is part of pandas, of course. We pass cat_s to it, and we specify the data type float. And this converts this one-dimensional categorical data into a data frame containing the dummy variable. So effective data preparation can significantly improve productivity by enabling us to spend more time analyzing data and less time getting ready for analysis. So we covered a number of different approaches we can take in order to prepare our data for further analysis, and that's what we're going to do in the upcoming videos. We learned how we can prepare and clean our data for further data analysis. This can help us save a lot of time at later stages. In the next video, we're going to explore pandas joining and grouping functionality. If you haven't already, feel free to subscribe to the channel to not miss any videos. See you guys in the next video.